In a previous video, we summarized the behavior of a MOSFET that is specified by a Kn and Vt by first determining VGS and VGS at this voltage, gate to source, and this voltage in the channel VDS. If VGS happened to be below Vt, the transistor was in cutoff, and ID, this current, was 0 amps. Otherwise, we needed to compute the overdrive voltage VGS, this 1 minus Vt, and compare VDS, the channel voltage, with that overdrive voltage. If it was below that one, the transistor was said to be in triode mode, and it had a conductance given by this expression. It was a function of the overdrive voltage, a function of the V gate source voltage. Otherwise, if VDS was above the overdrive voltage, we said the MOSFET, the transistor, was in saturation mode, worked as an amplifier, and the drain current was 1/2 the conductance coefficient multiplied by the overdrive voltage squared. That is to say that the drain current is a function of VGS according to the definition of the overdrive voltage. Let's go into some tutorial time. Consider this circuit here. The gate has been grounded. It's connected to the reference node, and we have a power supply with 2.5 volts on the top and negative 2.5 volts on the bottom. We are told here we have an NMOS transistor, that is shorthand for an N-channel MOSFET. The transistor is specified by a threshold voltage of 0.7 volts and enough data to compute Kn, the conductance coefficient. Determine Rd, this resistance on Rd, if we know this current is 0.4 milliamps and this voltage is 1/2 a volt. Well, for the resistor and the drain, we can use Ohm's law to compute its value. You see, we have 2.5 volts on the top and 1/2 a volt at the bottom, and we have the current through it. Ohm's law, that means that Rd is 2.5 minus 0.5 divided by the current, 0.4 milliamps. That resistor's value is 5 kilo ohms. What about the other? What about the one at the bottom? Immediately we think, if only we knew Vs, we could do exactly the same trick, because after all, the current here in Rs is the same 0.4 milliamps. We have the voltage at the bottom, negative 2.5. We only need Vs. What is Vs? Okay, if we knew Vs, we could do the same trick to compute Rs. That's right. Let's explore this idea. We can compute VGS, the gate to source voltage, and from there we can find Vs because Vg is 0, right? How are we going to do that? Oh, well, let's do this. Let's assume that the transistor is in saturation mode. That means that the drain current is given as Kn divided by 2 multiplied by the square of the overdrive voltage. What do we know there? We know ID. ID, the current in the drain, is 0.4 milliamps, this value. Kn we can compute. We have Vt is 0.7 volts given up here. Oh, we can compute VGS. This is a quadratic equation. It's very easy to find that, right? Kn is 3.2 milliamps per volt square. I've used the values given as part of the problem. We enter that and we have an equation with only one unknown, VGS. It's a quadratic equation. We solve it and we get two possible answers. VGS mathematically could be 1.2 volts or 0.2 volts. However, of those two values, only one is possible, only 1.2. I invite you to check why 0.2 does not work. Why is that? Oh, because if it was 0.2 volts VGS, it would be below Vt, and the transistor would be in cutoff, and the current ID would be 0, and we are told it is not 0. So you see why I say it's impossible that VGS is 0.2 volts. So the right answer had to be 1.2 volts. 1.2. Now that we have that one, we can follow our plan and we say VGS is 1.2. G is higher than S by 1.2 volts, but G is at 0 volts. So VS is negative 1.2 volts. Perfect. We know the voltage here is 1.2 volts. The voltage here is negative 2.5 and the current through is the same on the top, 0.4 milliamps. Why? Because the gate current is 0. Fine. We say the resistor RS is negative 1.2 Vs minus 2.5 volts divided by the current 0.5 milliamps. That means this resistor is 3¼ kilo ohms. Another tutorial exercise. In the figure, a current mirror, this one, both transistors are identical. Both of them have the same threshold voltage, half a volt, and the same parameters that allow us to compute the same Kn for both. Find the values of those two resistors so that VD1, the drain voltage of the transistor on the right of Q1, of the NMOS on the right, is 0.8 volts. That value is given, 0.8 volts. And we're also told that Q1, the NMOS on the left, is operating at the edge of saturation, so that means that VDS, this voltage, is exactly equal to the overdrive voltage. Okay. Let's see. VD is 0.8, that's right. VDS is 0.8. But because of this wire here, VG is also 0.8. Because VS is 0, VGS is 0.8. So you see we have a lot of information. The overdrive voltage for Q1 is VGS minus VT. VGS is 0.8. VT is 0.5. 0.8 minus 0.5. The overdrive voltage is 0.3 volts. And then we check VDS. VDS in this case is also 0.8 volts, and that is more than the 0.3 volts of the overdrive. So this transistor Q1, the NMOS on the right, is in saturation. If it's in saturation, we know that the formula for the drain current is this one. Okay, observe, we know Kn, or at least we can compute it. We know the overdrive voltage, that is 0.3, and we can compute what is that drain current. Kn is given here at the top, 1.6 milliamps per volt square. And then we replace that here and compute what is the current in the drain of Q1, that is 72 microamps, this current up here. Let's compute RD1. We know this is 1.8, the voltage here is 0.8, and we know the current in the resistor is 72 microamps. With those three values and Ohm's law, we find RD1 to be 13.9 kilo ohms. What about the other transistor? The overdrive voltage for the other transistor is also 0.3. You say, how can you say that? Well, VG for Q2 is also 0.8 volts. This is VGS. VT is the same value as the other, 0.5. So V overdrive for Q2 is also 0.3. But we are told that Q2 is operating at the edge of saturation. So that means that VDS, this voltage, is 0.3 volts. Okay. If that is 0.3, that means that this node here is at 0.3 volts. What else? Okay. At 0.3, so that means that we can use the saturation mode formula to compute what is the current in the drain. Let's compute it. That voltage is 0.3, and the drain current for that Q2 is also 72 microamps. Now you see why we call this a current mirror. This Q2 it's a mirror of Q1 in terms of current. Now we can compute RD1. 1.8, the voltage on the top, minus 0.3 divided by the current through, which is 72 microamps as well, is 20.8 kiloohms. This is what's called a current mirror. So far, we have been using EMOS with an N channel. Sure, the body was a P-type material, but the channel that was formed was rich in electrons, so it was an N-channel transistor. If we exchange all P materials for N materials and vice versa, we have a P-channel transistor. We could do that. All voltages and all currents would be reversed, and all voltage conditions have to be reversed too. VT is negative for a PMOS, and so are VGS and V over drive. VDS, the drain to source voltage, the channel voltage, is also a negative value for a P transistor. The conditions are, for saturation, VGS has to be below the threshold voltage, both of them are negative numbers, and VDS have to be below the overdrive voltage, and both of them are also negative values. Consider this PMOS here. You say it's a PMOS? Sure. You see the terminals gate, source, and drain. The source, I drew it at the top, and the source identified by the arrow, but this diagram has the arrow pointing into the channel because this is a PMOS transistor. Okay. Now the values. I'm telling you that this source is 3 volts like that, and this is 7 volts, and the transistor is specified by this conductance value and this threshold voltage. -1 because this is a PMOS. Okay. My question to you is, what is the mode of operation of that PMOS? Let's see. VGS is -3 volts according to this. -3 volts is below -1 volts VT. So that means that there is a channel, there is current in there. Let's see what else. VDS, according to this source, is -7 volts. Okay, -7 volts, that's right. This is VDS, -7 volts. That's good. But -7 is also below the overdrive voltage, that is -3 minus -1. Okay, that is -2. -7 is below -2. So this transistor is in saturation. That is what I wanted you to answer. Another problem. Let's substitute the source by a 1.5 volt source. What is the state of operation of the PMOS? Same transistor. You say, okay, the overdrive voltage again is going to be -2. Same conditions. But VDS, this one, VDS, is only -1.5. That is not below the overdrive voltage of -0.2, so that means that this transistor is in triode mode, and we have to use the triode mode formulas. Let's introduce another combined device that is very popular in computer applications, a complement MOS pair of transistors. The C comes from complementary. We have 2 transistors manufactured side by side on the same stratum. One of them is an N-channel transistor, the one on the left, and the other is a P-channel transistor, the one on the right. Please observe that the N-channel one is built on top directly of a P-type body. Here we will enhance the channel region and make it rich with electrons borrowed from the source and the drain wells. The opposite happens in the PMOS. Let's do something with that CMOS pair. Tutorial time number 6, a CMOS example. We have a CMOS pair, where both transistors, they share Kn, and Vt is 1 volt. So that means negative 1 volts for the PMOS and positive 1 volt for the NMOS at the bottom. For several inputs, this is the input. 0 volts, 2.5, negative 2.5. In each case, determine V0, the output voltage, and determine also this current ID in the PMOS, in the transistor at the top QP. The question is that configuration what we called a logical NOT gate? Let's see. A convention. In this exercise, any voltage above 2 volts will be considered a true value, and any voltage below negative 2 volts will be considered a false value. So that means that when we apply 0 volts, we have neither a true nor a false. Well, let's do that anyway. The input is 0 volts. If the input is 0 volts, we can compute VGS for the PMOS transistor at the top, and that is 0 minus 2.5, that is negative 2.5 volts. And we could also compute VGS for the NMOS at the bottom, and that is 0 minus 2.5 volts, that is positive 2.5 volts. Okay, you say there is symmetry in that circuit. Symmetry in this case implies that we have exactly the same current in the drain on the top transistor and on the bottom transistor. So this current goes like this, and this one goes like that. And out of symmetry, those currents have exactly the same value. Okay, what is the implication? The implication is that the current in this resistor is 0 amps. But according to Ohm's law, in a resistor, the current is 0 only if this voltage is 0 volts. That is right. That is the meaning of that. That current and this current, they are the same. That means that this current is 0 amps. The implication is that V0 is 0. That means that VDS for the PMOS, this voltage will be, this is 0, V0, and this is 2.5. That means that VDS for this one, this is drain, and this is the source, and that is negative 2.5. And for the one on the bottom, you say this is a drain, and this is the source, and that voltage is 0 minus 2.5, VDSN is plus 2.5. But the overdrive voltage will be 2.5 minus VT, minus 1 volt that is given, that is 1.5 volts, which tell us that both of those transistors are in saturation. So you see, the one on the bottom has a 2.5 volts, and that is above a 1.5 volts. This one is in saturation, and the one on the top have a VDS that is negative 2.5, and that is below the overdrive voltage of QP, that is negative 1.5 volts. We can use a saturation formula to compute the current in either of them. 1/2 Kn, that is 1 milliamp, multiplied by the overdrive voltage, 1.5 squared, 1.13 milliamps. And that answers the first part of that question. Now, let's answer that when we enter a true and later a false and see what is the output. We enter a true, plus 2.5 volts up here. Let's analyze the circuit. The voltage at the top, this one, will be 2.5 minus 2.5 is 0 volts. That's right. That is the gate source voltage of the top transistor. But that signifies only one thing. If VGS, in this case 0, is above the threshold voltage for the PMOS, which is negative 1 volt, that means that this PMOS is in cutoff. That is in cutoff. P is in cutoff. This current at the top is 0 amps. That means that I can erase the top of the circuit without prejudice. Alright, let's analyze the bottom circuit. For the bottom circuit, the voltage VGS is directly minus 2.5 minus 2.5, that is 5 volts. 5 volts, that is above 1 volt the threshold voltage, so there is current in this second one. That's right, VT is 1 volt. The overdrive voltage will be 5 minus 1, 4 volts. Let's compute now this voltage here. I'll show you that this voltage, drain to source, is actually less than 2.5 volts. If it's less than 2.5 volts, there is no way on earth that is going to be above the overdrive voltage. So this transistor cannot be in saturation, has to be in triode mode. Let's do that graphically. That is a drain current, and this is the drain to source voltage of the NMOS. Here is the load line with a slope of -1/10,000 ohms, which is the value of this resistor. In that graphic, we have down here at this intersection the value of the source that feeds the circuit, which will be positive 2.5 volts if you look at the loop carefully. That's right. And the quiescent point will be here somewhere. Wherever that is, you agree with me that this voltage, VDSN, is going to be less than 2.5 volts. Oh, alright. If VDSN is less than 2.5, that means that VDSN is less than the overdrive voltage 4 volts, right? And that means that that NMOS is in triode mode. That is correct. We could compute that current as 2.5 minus VDSN, that I don't know what value it is, divided by the resistor 10,000 ohms. But knowing that it's in triode mode allows us also to use this triode mode formula to compute the current in there. But we already knew that IDN is 2.5 minus VDSN divided by 10,000. We saw that previously. Well, we replace this one, we substitute that with this expression, enter that in the calculator in a single equation as you see, and now we have one equation with one unknown only, VDSN. But this is a quadratic equation, no problemo. We solve for that and we get two possible values for VDSN. Which one is correct? Immediately we realize that the 8 volt solution is not realistic. If this current were 8 amps, that would mean that the voltage VDS would be negative. That means that the transistor is delivering power in here, and that is not what happens. This is just a resistor in the eyes of the rest of the circuit. So the right value for VDSN has to be 61.4 millivolts. Now that we found that voltage, this one is 61.4 millivolts, then V0 is negative 2.5 plus 61.4 millivolts. That's right, that value here, V0, this one is negative 2.44 volts. But that, according to our rules, is below negative 2 volts. This is a false value, false. So that means that in this circuit, when we enter a true, the output is a false. So far so good. This is half of the behavior of a NOT gate. What else do we have? The input is true, the output is false. Let's try now with an input that is false. It's negative 2.5 volts, this one. A similar analysis to the previous slide tells us that this time the NMOS, the transistor at the bottom, is in cutoff. The same analysis will tell you that the output voltage is 2.44 volts. It's a true one. So indeed, when the input is false, the output is true. This circuit is a logical inverter, a NOT gate. What happens when we want to use the MOSFET for amplification? The first thing we have to do is making sure that the MOSFET is in saturation mode. We need to bias the MOSFET. Biasing the MOSFET is to guarantee that it is working in saturation. We'll use this circuit. Having a voltage divider on the gate size allows us to use a single voltage source for the drain and for the gate to apply VG and VGS. That works because the current in the gate is zero. We have a perfect voltage divider. On the other side, this resistor provides a negative feedback. When the current in the drain, this current increases, that current, this voltage also decreases, which means that VGS will be smaller and that will reduce the drain current. Let's see that again. Remember that Vs, this voltage is given by Ohm's law, is Rs, this resistor, multiplied by this current, ID is the same current, right? And VGS is Vg, that is constant in this circuit, minus Vs, the one on the top. Apart from that, we know that in saturation, the drain current, this one is given by this formula that depends on VGS. Now, what I'm saying is that when ID goes up, because the characteristics of the transistors changed, then this voltage Vs also goes up because Rs is a constant. But if Vs goes up, because Vg is constant in this circuit, then VGS will decrease. But if VGS decreases here, then ID decreases. So you see the circuit is self-stabilizing, and we say that this source resistor is a negative feedback resistor. A rule of thumb: we design this circuit so that the voltage VDS is approximately half the voltage of the source at the top. And of the rest of the volts, well, we allocate 1/8 of them approximately to this resistor at the bottom. Tutorial time number 7. Let's apply what we've learned. The NMOS transistor, this one, is specified with a threshold voltage of 1 volt and a Kn of 1 milliamp per volt square. Determine all node voltages and all branch currents. Well, let's make this not a tutorial time, but rather quiz time. I want to know how much you've learned of these videos. So I'm counting on you to solve this circuit. Pause the video, solve the circuit, and then press the key to continue. At this point, I expect that you've already solved the circuit, and we can work this solution in comparison to the one you did at home. Vg will be given by a voltage divider, 10 multiplied times 10 divided by 20, that is half. The voltage VDD, that is 5 volts, that is right. And Vs, well, Vs is 6,000 times the current in the drain, whatever the current in the drain is. We don't know what it is. VGS is going to be then 5 minus 6,000 times ID. The overdrive voltage is VGS minus VT, that is 1 volt. Okay, so that means 4 minus 6,000 times ID. Because we are assuming the transistor is in saturation, that is the point of this circuit, ID is given by the saturation formula as a dependence of VGS. Substitute the overdrive voltage here. Observe that this is a quadratic equation in ID. We know everything else. We enter that equation in the calculator. ID, this is Kn, this is the overdrive voltage, 4 voltage minus 6,000 times ID squared. We solve that quadratic equation and get 2 possible answers. I invite you to work out how to discard one of them and determine that the actual solution is the second one. Approximately half an amp. 0.544 milliamps, 544 microamps. Well, if you use that to compute the overdrive voltage. This formula over here, the overdrive voltage will be 4 minus 6,000 times that current, that is 0.737 volts. And you proceed to compute VDS. And with VDS and the overdrive voltage, you say, well, VDS is above the overdrive voltage, so indeed the transistor is in saturation and my computation is a valid 1. Before we leave, let's compare this new transistor, the MOSFET, versus the one we studied in our previous term, the BJT, the bipolar junction transistor. We created a table, on one side the BJT, on the other side the MOSFET. We begin with a symbol. The symbol we use for the BJT, at least for the NPN BJT, is this one. In it we identify the base, the emitter, and the collector, and the output current is a collector current. The current in the collector is transported both by holes and electrons, so that means that current is a bipolar current. In the MOS, the symbol we use is this one, at least for an N-channel MOSFET. The terminals are the gate, the source, and the drain, and the current of the output is the drain current. The current is formed mostly in this transistor by electrons, so we call this a unipolar transistor. When we use them both for amplification, the BJT has to be in its linear or active region. The MOSFET has to be in its saturation or active region. The BJT's base to emitter voltage is 0.7 volts, but in the MOSFET, the gate to source voltage has to be above the threshold voltage, so there is a channel. The collector to emitter voltage is above the saturation value of 0.2 volts in the BJT, but in the MOSFET, the drain to source voltage is above the overdrive voltage. The output current of the BJT, the collector current, is linearly proportional to the input base current. In the MOSFET, the output current, the drain one, depends quadratically on the overdrive voltage. The input base current is very small in the BJT. In the MOSFET, the input current, the gate current, is absolutely zero. Now, if we use those transistors for a digital application, the BJT switches between its cutoff mode, in which the base to emitter voltage is below 0.5 volt, and a saturation, in which the collector to emitter voltage is fixed at 0.2 volts, as we saw in our previous term. The MOSFET switches between cutoff, in which VGS is below the threshold voltage, and triode, in which VDS is below the overdrive voltage. And that, my friends, is all. Thank you very much.